Hey guys, today we are going to discuss fluid flow by Wasser Derek. Thank you. We are going to start with the derivation of the Toricelli flow. You know Toricelli flow acts for containers with no pipes. In other words, it acts for containers with orifices, as shown in the slide. Now, before you derive the Toricelli flow, we are going to consider the diagram in the slide of a piped system, as shown in the slide. Let's continue. The differential element shown in the previous slide is acted upon by pressures P1 and P2, and is also acted upon by shear stresses. Now, we're going to conserve energy changes on that differential element. We're going to say P1 minus P2 times the volume is equal to kinetic energy gained by the differential element plus work done against viscous forces. The work done against viscous forces is given by a half COAS rho v squared times L plus a half C1AS rho v squared L. Now, AS is the surface area, dV is the differential element, the volume of the differential element, and P1 minus P2 is equal to the pressure, H rho G. Now, the coefficients CO and C1 are given in the slide. CO is equal to K over Raynaud L, and C1 is equal to 16 over Raynaud D, where Raynaud L is equal to rho VL over coefficient of viscosity, and Raynaud D is equal to rho VD over coefficient of viscosity. After I substitute for C1 and CO, we get the final expression as 2GH is equal to V squared plus 16 mu L over R squared V rho times V squared plus 2K mu over rho RV times V squared. Now, for Toricelli flow, we substitute L is equal to 0, and we get. Now, we've got the final equation of Toricelli flow. From experiment K is approximately equal to 1142.58. Now, to get the velocity equation, we make V the subject of the above formula. We get the expression of velocity in terms of all the other variables. Thank you. For Pouiselle flow, we bring back the other equation which we derived earlier on, which is 2GH is equal to V squared plus 16 mu L over R squared V rho times V squared plus 2K mu over rho RV times V squared. Now, of course, we divide through by V and remain with that equation, a quadratic equation of velocity. Finally, using the Pouiselle formula, we get the final equation of velocity. Now, we factor out from the square root that factor shown in the slide. Now, we recall from binomial expansion that 1 plus x to the power n is approximately equal to 1 plus nx for x far less than 1. Now, by comparison, we have n is equal to 0.5, and we have x is equal to 8gh over that factor squared. Now, we are going to use binomial expansion, provided x is far less than 1. Let's continue. Now, for x to be far less than 1, the length has to be very large, and the radius has to be small. Even the viscosity has to be very large for x to be far less than 1. Now, if that condition is met, we use the binomial expansion. We bring the half from the power and we bring it inside the brackets. And for Pouiselle flow, we have 8L over R plus K is approximately equal to 8L over R. Now, substituting all the above, we end up with the equation of velocity, from which you can get the equation of flow rate, which is the Pouiselle flow. You can go ahead and simplify and verify that actually that's what we get. Thank you. For turbulent flow, the factor in the square root is far greater than 1. And the summation 1 plus that factor in the square root, we end up with the factor itself. The 1 goes away since the factor is far greater than 1. Now we end up with an equation of velocity shown there in the slide, which is 2v is equal to negative 2 mu over r rho into brackets 8l over r plus k plus 2 mu over r rho into brackets 8l over r plus k and the square root of 8gh over 2 mu over r rho into brackets 8l over r plus k, the whole of it squared. Now after simplifying, the equation of turbulent flow looks as they are given in the slide. That's the equation of velocity for turbulent flow. Thank you very much. For more information about fluid flow, you can hit on the link provided in the description for further work about fluid flow. Thank you very much.